Hello, in this video we would like to talk about the normal or the Gaussian distribution. The normal distribution is probably the most important continuous distribution, and as you will see it has this kind of format, bell-shaped form, the PDF of the distribution, and it is used widely in many different scenarios and applications. For example, in engineering, when we want to model measurement errors, in communication systems when we are modeling noise in the system, or in scenarios when we look at the distribution of height of people in a given population, or the IQ of people in a population. We usually see this kind of curve. So it is used in many different scenarios, and we will see this curve again and again in applications. So the question is why? One way to answer that question, one way to explain this phenomenon is the central limit theorem, CLT, that we will discuss in much more detail later on. Basically, the CLT roughly states that if you add a large number of random variables, the distribution of the sum will be approximately normal under certain conditions. So if I have a large number of random variables, x1 plus x2 up to xn, and under these certain conditions, I can say that the sum has normal distribution. So the PDF of the sum is going to look like this PDF that we have here. And we can argue that in real life, systems are complex, and when we look at a random variable, it's a large number of factors impact that random variable. So we can look at that random variable as a summation of a large number of random variables, and that's why many random variables in real life has normal distribution. So we will discuss the central limit theorem in more detail later on. So the point is that the normal random variable appears a lot in practice, and it's very important, so we want to study its properties. Okay, so let's talk about the PDF and CDF of the normal distribution. The normal distribution, when we say x is normally distributed, it has two parameters. So it has a mu and sigma. As we'll see, mu is its average, sigma is its standard deviation. Now, it is easier to look at a specific case when the mu is 0 and the sigma is equal to 1. And we call this the standard normal random variable. And the reason we do that is that we will see later on that we can produce any normal random variable with any mu and sigma from the standard normal. So we can convert the standard normal to any other normal distribution. So it's better to first understand the standard normal, and then we can convert it to any other normal that you want. Okay, so this is our notation. We say that z is the standard normal random variable, or it has the standard normal distribution. We write it like this. If its PDF is given by fz of x is given 1 over square root 2 pi e to the minus x squared over 2 for all x. Okay, so that's basically the curve that we saw. If you plot the curve, it's going to look like this. I mean, it's going to be symmetric around 0. So maybe I can try to plot it better. Anyway, so it decays exponentially as you move away from 0. And this is a formula. Fz of z is 1 over square root 2 pi e to the minus z squared over 2. Now, what is this square root 2 pi? It's just because we want to normalize it so that the total area under the curve becomes 1. So basically, we need to have the integral from minus infinity to plus infinity, fz of x dx, that must be equal to 1. And that's why we need this factor 1 over square root 2 pi. And it is shown in the text book that the constant must be 1 over square root 2 pi. Okay, so how about the CDF? Well, the CDF is simply fz of x is by definition probability that z is less than or equal to x, which is the integral from minus infinity to x fz, the PDF fz of x dx. Now, because the normal random variable is very important, we give the CDF of the standard normal a specific name. We call it phi of x. Okay, so we just call it phi of x. Phi of x is the CDF of the standard normal. So basically, it is the area under the PDF curve So if you look at the figure here, if this is my standard normal PDF fz of x, then for any x, if you look at in this area that is shaded in this figure, that tells me that is going to be the phi of x, or the CDF at point x. Now from this figure we can kind of conclude some properties of the phi function. First of all, if you look at it, because there is symmetry here, if you integrate until point 0, the integral must be equal to 1/2, because the total area is 1, so half of it is going to be 1/2. So we conclude that phi of 0 is going to be 1/2. So that's here. If you let x to be a very small negative value, this area becomes smaller and smaller, and the phi approaches 0 as x goes to minus infinity, and that's what we expect. Note that phi is just a CDF, and CDF of x as x goes to minus infinity always becomes, the limit always becomes 0. So that's another property. And of course, as we move to large values of x, the CDF approaches 1. So these properties, we are summarizing them here. The limit as x goes to infinity becomes 1. The limit as x goes to minus infinity becomes 0. Phi of 0 is 1/2. And the last one, we want to show that phi of minus x is equal to 1 minus phi of x. Why is it true? Well, what is phi of minus x? If this is x here, minus x is here, so I am looking at phi of minus x is this area. But because of the symmetry, this area is the same as this area, right? So if I add phi of minus x, so let me just write it, and this area is phi of minus x. If we add phi of x plus phi of minus x, we get the total area under the curve, which is 1. And that's why phi of minus x is 1 minus phi of x, and that is a useful property to know. So these are just some properties of the phi function. And because this phi function is an important function, it is usually available in calculators, software packages, and so on. So in MATLAB, for example, you can use the command norm CDF to get the value of phi of x. Okay, so let's talk about the expected value and variance of the standard normal distribution. Well, first of all, let's talk about the expected value. What is the expected value of x? Or in particular, let z be a standard normal random variable. What's going to be its expected value? When I was introducing the standard or generally the normal distribution, I mentioned that it has two parameters, mu and sigma, and mu is expected value. So we expect that the expected value to be 0, and that is true. So if you think about it, basically the PDF curve again is is a symmetric curve, 1 over square root 2 pi e to the minus x squared over 2. So expected value of z becomes integral from minus infinity to plus infinity x 1 over square root 2 pi e to the minus x squared over 2 dx. And if you think about it, this is an odd function, right? If you change x to minus x, you get the negative value. Now why is it important? If you have an odd function like this, odd function means that, again, if you have a function for which f of x is equal to f of minus x is equal to minus f of x, then we call it an odd function, right? So this is an odd function. It looks like this. So if you have x and then you look at minus x, the value becomes negative to that. Now this is an odd function. I am integrating from minus infinity to plus infinity, and then I get two parts, and both of them are finite, but this part cancels this part. So basically this integral becomes 0. And that's what we expect. As I said, this mu is the expected value, so for the standard normal random variable, the expected value is going to be 0. So how about the variance? To find the variance, we can write variance of z is equal to expected value of z squared minus e of z squared, but this is 0, so it's just expected value of z squared. To find expected value of z squared, we can write expected value of z squared is equal to integral from minus infinity to plus infinity x squared 1 over square root 2 pi e to the minus x squared over 2 dx. Now this is an even function, so we cannot say it's 0. It's not 0, it's positive. And we can find this by using, for example, integration by part, which is done in the text. And if you do that using integration by part, we find out that this value becomes 1. So the conclusion here is, if z is standard normal, then its expected value is going to be 0 and its variance is equal to 1. So now we want to extend this discussion to the case when we have a general normal random variable, right? I want a random variable x, which is normal, with parameter mu and sigma, such that expected value of x is equal to mu and variance of x is equal to sigma squared. So its standard deviation is sigma. So usually, there are different notations. Some books use n and mu of sigma. Some books use normal with mu and sigma squared. So sometimes they show the variance here. So I think at the beginning, when I was writing this, I just wrote sigma, but I believe the notation sigma squared is more common. So we can write it as normal and mu and sigma squared. It's just a matter of notation, and different books might use different notations. The point is that we have two numbers, mu and another number, sigma, which is the standard deviation. Okay, so if I want to have a general normal distribution with a given mu and sigma, how do I define it, or how do I generate such x? Well, we can relate it to the standard normal. Basically, what I'm going to say is that if you get a standard normal random variable and then multiply it by sigma and then add mu, then call it x, then x is a normal random variable with parameters mu and sigma squared, right? Variance sigma squared. Why is that true? Well, first of all, what's going to be the expected value of x? Well, it's going to be, by linearity of expectation, it's going to be sigma, because sigma and mu, remember, these are just constant numbers. Sigma expected value of z plus mu, but expected value of z is 0, so it becomes mu. And how about variance of x? Remember, we had this rule that if we add something to a random variable, it doesn't change the variance. But if we multiply it by sigma, the variance of x becomes sigma squared variance of z. But variance of z equals 1, so this becomes sigma squared. Okay? So if I define a random variable x as sigma times z plus mu, where z has the standard normal distribution, I showed that its expected value is mu and its variance is equal to sigma squared. Now we define this as a normal random variable with parameters mu and sigma squared. So here is the definition. If z is a standard normal random variable and x is given by sigma times z plus mu, then x is a normal random variable with mean mu and variance sigma squared. Now I just defined it in terms of z, but I need to give you the PDF and CDF. What's the PDF and CDF of x? Well, we can find this from the CDF and PDF of z. For example, what is f x of x? The CDF of a random variable that is defined in this way is the probability that the random variable x is less than or equal to x, which is equal to the probability that we can replace x by sigma times z plus mu less than or equal to x, which is given by probability that z is less than or equal to x minus mu over sigma. Now this is CDF of z at point x minus mu over sigma, right? It's the probability that the random variable z is less than this x minus mu over sigma. And this CDF, we know what it is. It's the phi function, phi of x minus mu over sigma. Okay? So we say that if x is normal with mu and sigma squared, then its CDF f(x) of x is phi of x minus mu over sigma. How about its PDF. Well, the PDF is just a derivative of the CDF, so fx of x is d dx phi of x minus mu over sigma, and this becomes 1 over sigma chain rule in calculus, phi prime of x minus mu over sigma. But the derivative of the phi function is basically the PDF of the standard normal, so 1 over sigma the fz of x minus mu over sigma. And remember, fz of x, or fz of any value u, was 1 over square root 2 pi e to the minus u squared over 2. So the conclusion is that fx of x, you can write it as 1 over sigma square root 2 pi, we have a sigma here, e to the minus x minus mu, and you can write it as this, 2 sigma squared square. Okay, so that's the PDF of a random variable x that is normally distributed with parameter mu and sigma. So we could start from here. We could say that in general we say that x is normal if its PDF is given by this, and then define the standard normal as a random variable, normal random variable with mu 0 and sigma equals 1. So if you put mu equals 0, sigma equals 1, you get the standard normal PDF. So that's another way of doing it. Okay, so let me summarize. So in general, so this kind of summarizes all the PDFs and CDFs. If x is normal with parameter mu and sigma squared, then its PDF is given by this formula. Its CDF is given by this, which is the phi of x minus mu over sigma. And of course, from this you can easily compute probability that x is between a and b is simply fx of b minus fx of a, which is given by these, phi of b minus mu over sigma minus phi of a minus mu over sigma. So it is important to be able to work with this phi function and solve problems using these phi functions when we have a normal random variable. So let's look at an example to make sure that we can work with this phi function. So x is normal with parameter mu equals minus 5, and here I mean sigma squared. So sigma squared equals 4, which means that sigma is equal to 2. So my question is, first find probability that x is less than 0, find probability that x is between minus 7 and minus 3, and find the probability that x is larger than minus 3 given that x is larger than minus 5. Okay, I suggest that you solve this problem before watching the rest of the video. Okay, let's look at the solution. Part A. What is probability that x is less than 0? Well, this is by our formula phi of 0 minus mu over sigma, right? But what is mu here? Mu is minus 5, so 0 minus minus 5 over sigma. Sigma equals 2, so this becomes phi of 2.5. And if you use a calculator or MATLAB or whatever, you can see that the value of phi of 2.5 is approximately 0.99. So that probability is very close to 1, and that makes sense. Note that for my random variable the mu is minus 5, so the PDF curve, it looks like this, right? And I'm asking what's the probability that is less, the random variable is less than 0. Basically I'm asking what is the probability of this region, which is very small. I'm asking what's the probability of this region, which is very large. It's like close to 99%. The probability of this region is basically 1%. Okay, so how about the next part? Part B, probability that x is between minus 3 and minus 7. Well, this is phi of minus 3 minus mu, which is minus 5, divided by sigma, which is 2, minus phi of minus 7 minus minus 5 over 2, which simply becomes phi of, I believe, 1 minus phi of minus 1. And we can use the rule that we had. Phi of minus 1 is equal to 1 minus phi of 1, right? So this is 1 minus phi of 1. So it becomes 2 times phi of 1 minus 1. And if you look at the, use a table or use a calculator, you see that this is around 0.68. And finally, what is the probability that x is larger than minus 3 given that x is larger than minus 5? This is by definition of the conditional probability that x is larger than 3 and x is larger than minus 5 divided by probability that x is larger than minus 5, which is equal to probability that x is larger than minus 3 over probability that x is larger than minus 5, which is, well, we can write it in terms of the phi function, 1 minus phi of minus 3 minus minus 5 over 2, 1 minus phi of minus 5 minus minus 5 over 2, which becomes 1 minus, this becomes 1 phi of 1 divided by 1 minus phi of 0. And again, you can find the value of this. This is around, I believe, 0.32. So the point is that we should be able to use the phi function to solve, probabilities, to find probabilities regarding a normal random variable x. And finally, I would like to talk about an interesting property of a normal random variable, which is if I have a normal random variable with parameters, let's say mu sub x and sigma squared of x, and then if I have another random variable y which is equal to a times x plus b, basically I have a linear transformation of x, then y is also going to be normal, and we can find its mean and its variance. First of all, what is the mean and variance of y? Well, the mean of y is a by linearity of expectation, a times e of x plus mu, which is basically a times mu sub x plus b, and variance of y again is a squared variance of x, which is a squared sigma squared of x. Okay, but why is y normal? You can prove this in different ways. One way to do this is to write the CDF of y, which is the probability that y is less than or equal to y. Well, this is what? It's the probability that, by definition, ax plus b less than or equal to y, and becomes the probability that x is less than or equal to, well, let's assume a is positive, and then you can do the same for a negative. It's just the same idea. So if a is positive, this is the probability that x is less than or equal to y minus b over a. And well, what is this? This is the CDF of x, so we can write it in terms of the phi function, right? Basically, this is going to be phi of this thing minus mu of x divided by sigma of x, and you will see that this is exactly what we want. This is going to be phi of y minus a mu x plus b divided by a sigma of x. So this is the same as the CDF of a normal random variable whose mu is equal to a mu x plus b, and whose sigma squared, right, is equal to a squared sigma squared of x. Remember, I'm just using this thing here. I'm using our formula, this CDF. If a random variable has this sort of CDF, then it's going to be a normal random variable with parameters mu and sigma squared. So anyway, we can use this, we can prove this result. So it's a very useful result, and I think this has been proved in another way in the textbook. The bottom line is that, let me just summarize this. If I have a normal random variable, let's say I give you x is a normal random variable with parameter mu equals, let's say 1 and sigma equals 3, then I define another random variable minus 2x plus 1, then you can immediately say that y is going to be normal with mu of y is going to be minus 2 times mu of x, which is 1, plus 1, so minus 2 mu plus 1, and the sigma of y is just this value 2 times this sigma here. So sigma of y, sigma squared of y is going to be 2 squared times 3 squared. So y is normal with parameter -1, and sigma squared of y is 4 times 9, which is 36. Okay, so when we have a linear function of a normal random variable, we obtain another normal random variable, and this is a useful property that we can use it in some problems. Okay, thank you.